Hello, we're back for the practice exam. This is number 5. It deals with discrete time convolution. We're asked to find the overall impulse response of a cascade of systems, and we've been given the impulse response for both system 1 and system 2. H1 of n is given as un minus a shifted unit step function. H2 is a shifted unit step function minus another shifted unit step function. Part A, we're going to find the overall impulse response of the system, H of n. The way we're going to do this is by making use of the shifting property I have written here in blue. And the shifting property, of course, deals with the delta function, but both our functions are unit step functions. So the key here to recognizing why the shifting property is relevant for this problem is remembering that any discrete time signal can be represented as a series of delta functions. And that makes sense because we remember that a discrete time function is just a series of disconnected dots. So, of course, we can represent that as a delta. So let's transfer these functions into deltas. So we're going to start with h1 of n first. And here we have the unit impulse. And here we have un minus 2. It's a shifted unit. I'm sorry, I said unit impulse. It's a unit step function. It's a shifted unit step function. And it starts at 2. So we're going to take the difference of these, and we will get something that looks like this. That's 0, that's 1. Everything else is 0. So this is un minus 2. And you can see that we can represent this using delta functions as, delta n plus delta n minus 1. And that's our impulse response for system 1. Okay, let's move to system 2. The impulse response is the difference of these two unit step functions. So un plus 1 is a shifted unit step function. It starts at -1, it goes to positive infinity. Un minus 1 is a shifted unit step function. It starts at +1, goes to infinity. If we take the difference of these two, we are going to get a graph that looks like this. That's u of n plus 1 minus u of n minus 1, and that's equal to a series of delta functions, which we can write as delta n plus 1 plus delta n. Okay, now we need to find the overall impulse response. We have h of 2 and we have h of 1, both in their delta form. And we can see we've rewritten h of 1 and h of 2 right here. We want to find h of n right here. H of n is just h of 1 and convoluted with h of 2n. And this is because the systems are cascaded. So just so we're clear, the reason we're convoluting them is because h of 1n is the input to h of 2n. So the output is capital H of n. And that's of course just the convolution. So let's find h of n. Here we've rewritten the sifting property, and we are going to apply this directly. So h of n is equal to h of 1n convoluted with h of 2n. That's equal to delta n plus delta n minus 1, convoluted rather, no plus. Got ahead of myself there. Convoluted with h of 2, which is just given as dn plus 1 plus delta n. Okay, convolution is commutative, so we can FOIL this out like we would well, we can sort of FOIL it out like we would in algebra. We're still going to have the convolution operation, of course, but we can write delta n convoluted with delta n plus 1 plus delta n convoluted with delta n plus delta n minus 1 convoluted with delta n plus 1 plus delta n minus 1 convoluted with delta n. Now we can apply the sifting property. H of n is equal to, we're right here. In this case, we'll take x of n to be the first delta n, and delta n minus n naught to be the second delta n, plus 1. And n naught is then negative 1. So when we transfer that over, it's going to be delta n minus negative 1, which is plus 1. So we get delta n plus 1 for the first term. And for the second term, using the same logic, the first delta n is x of n, the second delta n is delta n minus n naught is 0, so we get delta n. Third term, we'll take delta n minus 1 to be x of n and delta n minus n naught to be delta n plus 1. In that case, n naught is -1, so we get delta n minus 1, that's this one, minus n naught, which is -1, so that's going to be +1. So, fourth term. Using the same logic, the fourth term is just going to be delta n minus 1. In this case, the second delta we took to be delta n minus n naught, and the n naught was 0, so we just get x of n, which we took to be delta n minus 1. Okay, so n minus 1 plus 1 is delta n, so this is delta n. So h of n, our overall unit impulse, or our overall impulse response, is then going to be 2 times delta n plus delta n plus 1 plus delta n minus 1. Okay, let's move on to part B. Part B asks us to find the output y of n if x of n is equal to a of n times u of n and a is between 0 and 1. We know that y of n is equal to x of n convoluted with h of n, which we just found in part A. And we can apply the sifting property again. I'll write it down just so we know what we're looking at. Since I went through the last example pretty slowly, I'm just going to apply it directly here without much commentary. Of course, convolution is distributive, so I'm not going to FOIL it out explicitly. You can just see we're going to go first term, second term, third term. Okay, so we get a n plus 1 times u of n plus 1, because we're replacing n with n plus 1 by the sifting property. And then we get 2 times a of n times u of n plus a of n minus 1 times u of n minus 1. So that's the equation for our output. Since we see all these unit step functions, this should tell you that this can be simplified into a nice little piecewise function. And you probably need to simplify it into a piecewise function to get full credit on the exam. our first case, since we have these shifted unit steps, consider this one first. So let's consider for n less than -1, and these are discrete functions, so remember we're only considering integer values. So for n less than -1, u of n plus 1 is 0, u of n is 0, and u of n minus 1 is 0. And if you have trouble seeing that, draw each function out, each unit step function out, and you'll see that there's 0. So y of n is 0. Okay. So at n equals 1, we know this first shifted unit step is going to become active. U of n will still be 0. U of n minus 1 will still be 0. So our function is equal to a of n is 1, remember. 1 plus 1 equals a of 2. And I think I might have made an error. Oh, sorry, I did make an error. N is minus 1 here. So a of minus 1 plus 1 is equal to a of 0, and any non-zero number, which a is because it's between 0 and 1, so it is non-zero, is just 1 if it's raised to the 0th power. Okay, so our next one that we want to consider is n equals 0. And at n equals 0, u of n plus 1 is active, and u of n is active, but u of n minus 1 is not active. It's 0, so we don't need to worry about the last term yet. Okay, so we get, I'm going to write it off to the side here, we get a of 0 plus 1 plus 2 times a of 0. So that's equal to a plus 2. So we get a plus 2 here. And the next one we want to consider is for n greater than or equal to 1, because we know once we get to 1 that all of our unit step functions are active. So I'm going to write this off to the side first. At n equals n greater than or equal to 1, since we're not saying explicitly what n is, we will keep a of n plus 1 plus 2 of an plus a of n minus 1 So we get a of n minus 1 plus 2an plus a of n plus 1. And that's going to be our final answer. So that was a long one. I encourage you to work through this problem as always by yourself and make sure that you can recreate this. And because you don't want to have to improvise on the exam. If you have to improvise an answer, you're probably going to spend too much time on it. So work through this and let me know if you have any questions. Okay, bye.